All right. Welcome to the 100. This is going to be a very fun lecture. Just before I start, it looks like that our Zoom has an issue that it stops itself before the start of the lecture. So we're trying to get that fixed. So thank you for all of those who are online and they rejoined the Zoom webinar again. Kind of telling you where we're at today and where we're going in the next couple of lectures is that we're starting actually digging deeper into the modeling phase of Data 100. So it's going to be really exciting. I'm going to try to do a lot of math derivation and also building different models with you and also evaluating the performance of different models with you throughout today's lecture and also in the next two lectures to come. So this is where we are. We're going to start by reviewing what you've seen in Data 8. We're going to start by taking a look at what was a simple linear regression and what is modeling and whatnot. And we're going to go a little bit deeper into more advanced models up to the point that in the last lecture of the regression sequence, we're going to talk about multiple regression. So what happens when you have multiple different attributes that you want to model and you want to combine them into predicting one variable. So this is a roadmap for today. We're going to start by talking about what is a model. Most of you might know what is a model, or like you've used the term that there is a machine learning model and whatnot before. But just to tell you what a model is from our perspective in Data 100 is that we always think about a model as an idealized representation of a system. So we say that it's an idealized representation of the system because it's not always accurate. We're not always considering all the details and all different features and all the noise that's involved in the system, but we're trying to actually have a model that kind of simulates or summarizes the trend that's happening in a system as accurately as possible. So an example of that could be modeling the fall of an object on Earth subject to constant gravity, that we always think about that as the gravity as being 9.81 meter per second square. But we all know that depending on the elevation, depending on the air resistance, this number is not accurate. So it's not going to be a constant model or a constant value that we can use in order to model the gravity. So this is an example that we simplify assumptions so that we have a model that's kind of roughly accurate. It's usable. It's simplifying all the dynamics in the underlying nature of the system that we have. And that's actually what we're going to do in Data 100 as well, because what you've seen in the previous lecture is that we want to model for population, but we don't have the population. We're trying to simplify assumptions, say that, okay, we're sampling, our data set is a good sample and is a good representation of the population, and now we're going to do the modeling. And not all of our data points are going to follow the trend that we're going to model. So those are kind of the noises that we're trying to also avoid or not directly model. So there's a famous saying by George Box that says, essentially all models are wrong, but some are useful, which is exactly what you should expect from all the modeling work that we'll be doing in Data 100 as well. So there are three reasons why we want to build models. And two of these reasons, you might see them in Data 100 this semester. Reason one is that there's a complex phenomenon that we want to actually model. So for example, we want to figure out how our parents' average heights related to children's average heights. So there's like all of those complex relationships that we can study directly, but we can actually collect a bunch of data and then model based on, or create a model based on those assumptions or those data points that we have. So in this case, what we would say is that the concept that we're modeling is very complex. What we want to have is a very simple model that is also interpretable, but it's also at the same time reasonably accurate. We don't want to throw in random kind of estimations of the values that we want. The second reason is that we might want to have really accurate predictions. We have a good amount of data. We want to make sure that we have very good, accurate predictions. And in doing so, what we will do is we'll throw in multiple different parameters, not multiple, but millions of parameters into a deep learning architecture, for example, in order to have a very accurate prediction. So what's happening when we want to use these black box models, because we call them black box models because there's millions of different parameters. It's not easily we cannot easily identify what's the relationship between them or what is the interaction between different parameters that spits out the actual estimation that we have at the end. But what we know is that over the population or over the sample that we have, we would say that it's accurate enough that we can actually use it. And it's more accurate than most of the interpretable models or simple models that we've seen in the first case. So examples could be if you want to have a spam email detection, right? So this is kind of a project that you will do in the last project of Data 100. We're going to give you emails with subject line, with the text in the body, and then you will be classifying emails into class of spam versus non-spam. What you want is you really want to be accurate here. You don't want to have a spam email landing in your inbox or vice versa, missing an important email and moving that into your spam folder. So this is very important. In these cases, we would say that the reason that we want to do the model is to have a very accurate prediction, even if it comes at the cost of the model not being interpretable. Reason 3 is a reason that we will not go over in Data 100, but that's a topic for more advanced courses, some stats courses, or Data 102 covers causal inference. So for example, if you want to figure out if smoking causes cancers, not correlation between smoking and a person having lung cancer, but figuring out the causation relationship between a variable and another variable or a response output. In those cases, we do causal inference. Again, not the topic for Data 100, but just so that you know that everything that we're modeling in stage 1 and 2 is mostly around finding a function that maps input to an output. But what we're looking at in the reason tree is to actually have a causal inference kind of argument and figuring out if a variable not only explains the output, but also causes the output. Again, I'll just go for Data 100. Throughout the explanation of this reason 1, 2, 3, I tried to say that interpretability is important and also accuracy is important. So what we'll try to do generally as data scientists is to strike the balance between interpretability and accuracy. So you really don't want to have a model. I mean, in some cases, we do have models that are not interpretable, but the best case scenario would be that if you have an interpretable model that is that at the same time is accurate enough for you to use as well. So common types of models. There are mechanistic models or deterministic models. These are models that generally follow a non-probabilistic view, meaning that there is a study or there are measurements, mechanistic measurements that we would do, such as, for example, the way that people arrived at Kepler's third law of planetary motion or Newton's law. And based on those measurements, they build the relationship between multiple different variables and they build those models. We call these models mechanistic or deterministic models. We call them deterministic because there is no probability involved. When they measure it, the values is there, and then they measure multiple different variables and they basically look at the relationship between them. There are models that are probabilistic. You will see one example of a probabilistic model towards the end of Data 100. And mostly we will see probabilistic models when we want to do classification or identification of a certain task. So an example of that, I brought it here from one of my papers that is the work of my PhD student looking into studying brain waves in order to figure out the anxiety levels of subjects, right? So brain waves by themselves are random processes that you're modeling. There are probabilistic models that basically you will try to study and figure out how they travel in brain and how they interact with each other and how would they concentrate in a certain area so that it causes anxiety or it causes, for example, seizure. This is kind of the modeling that they would do in order to predict whether someone is going to have an onset of seizure in future or not, just looking at those probabilistic models. And then you will basically have a probabilistic model that will say that with this specific likelihood, this subject that we had the recording of their brainwaves over the last, like, for example, 7 days is going to have seizure for example, in the next 10 minutes. And if that probability is high enough, then basically in patient facilities, they'll try to monitor that patient more accurately or more closely. So this is the kind of different categories of models that we're looking at. Mechanistic or deterministic, there's no probability involved, and probabilistic models that, again, you will see later on in Data 100. What we're going to do in Data 100 right now as a starting point, just to get warmed up, is to take a look at simple linear regression and what you'd seen in Data 8. So we're going to go over the regression line and the definition for a regression line and actually derive the equation for regression line that you'd seen. But this time we're going to actually use a little bit of calculus in this lecture to just get warmed up, because you will need to get comfortable with actually doing derivatives and calculating or optimizing an objective function and whatnot. And I'm going to tell you what objective function is by the end of today's lecture. So let's dive in. You've seen this regression line from before, right? So you've seen that in Data 8. This was a famous plot that you had that was predicting on different chapters of Little Women novel that using the number of period punctuations in a chapter, it was trying to predict the number of characters that would appear in that specific chapter. You would see that it tries to model it using a regression line, and then we're going to take a look at the equations for that regression line and how Data 8 arrived at that regression line. You also see that in Data 8, we defined a slope as correlation, or R, times the standard deviation of Y over standard deviation of X. This is your Y dimension, and this is your X dimension. And correlation, I'm going to formally define it in a sec. An intercept, we talked about intercept, or the point that when X is equal to 0, your Y value is non-zero, probably, or that's called Y-intercept, or intercept was defined as average of Y minus a slope times average of X. And we're going to see why that's the case. So you don't need to actually memorize all of these equations anymore. You just need to know two things about a model in order to drive all the equations yourself. So you're going to be released from memorizing kind of tasks from this point on. We also talked about regression estimation. So regression estimation is that, okay, you have a model, or estimation on any model per se, is that we have a model and we're gonna just plug in the value that we want to do prediction on into the equation, and the equation was intercept plus slope times the value, and then that would give you the regression estimation. There is a concept of residual that we're going to play a lot with, and residual is defined as observed value minus the estimated value. Okay, so the residuals are actually shown here on the plot. This is a residual, this is a residual, this is a residual, and so on and so forth. What we're trying to do in Data 100 and throughout the modeling is that we're looking at the residuals that we're accumulating throughout the entire data set, and we're trying to minimize the amount of residual. And I'm going to define what amount of residual means formally using a function, mathematical function, later on in today's lecture. But just know that if a point is not on the line, that's an imperfect prediction, and we're going to measure how imperfect it is, and we're going to try to make sure that the model that we're fitting to the data is passing through all the data points as accurately as possible. One observation here is that some residuals are positive, some residuals are negative. What you're seeing here is that, for example, for this specific data point, the estimation is exactly this, the actual value is this value right here on the y-axis. And the estimated value is the projection of that point onto the line, and then you would see what that value is, right? So this is my y, my ground truth y, and this is y hat. I put hat as a representation of this is the predicted value or the estimated value. And you can see that based on this equation, the residual is a positive value for the points that are above the line. And you can also rationalize in the same way that for any point that's below the line, the residual is a negative value. You will see later on that there is a relationship between all of these residuals that are positive and the residuals that are negative. And that's why the line generally passes through in the middle of the data point. So you have some positive residuals and some negative residuals. And we're going to see the mathematics magic behind why that's the case. So let's revisit correlation. So these are all reminders. So if you need a refresher, please go back and take a look at Data 8 or just calmly look at the slides after the lecture, and it will all make sense. What was correlation? So I want to break down the definition of correlation here for you. The definition from Data 8 textbook says that correlation is the average of the product of X and Y when both are measured in a standard unit, right? 3 pieces of information. And let me tell you what they are. It's starting from measuring in a standard unit. When we say that a variable is in a standard unit, that means that it's zero centered, the standard deviation of one, right? So the average of all the values should be 0, and then the standard deviation of all of the values should be equal to 1. And the way that we actually standardize the data is to go through this process right here, that you take one column of values or one set of values, you calculate their average, you subtract the average from each individual sample. So that's how you will make sure that it's zero-centered, meaning that the mean is at 0. And then in order to make sure that the standard deviation is equal to 1, you divide all of these transformations by a standard deviation of that entire column or that set of values. This ensures that the standard deviation is equal to 1 as well. So that's what we mean by a standardization. So that's a standard unit. So when we say product of X and Y, both measured in a standard unit, this means that X measured in a standard unit is right here. Y measured in a standard unit is right here. So that's X and Y measured in a standard unit. And then there was an additional piece that says that the average of those products. And you're seeing that here I'm taking average by summing up all of these products and then dividing it by 1/n, which is the average, right? So what is I, what is N? And let's go back to our data set. So I'm assuming that in this data set, I have a data frame with 2 columns. I'm going to call one column column X, one column Y, and then the rows are row 1, row 2, and then all the way to row N. So assume that I have N data points. This data set D has N data points with row 1 be X1, Y1, row 2 be X2, Y2, and then all the way to Xn, Yn. So what I need to do is go through each one of those rows, zero center or standardize all of those values. Once all of those values are standardized, I will basically try to calculate the product of the 2 X standard unit, Y standard unit in each given row, and then I have a value, and then all of those values need to be summed up together and then divided by or multiplied by 1/n to calculate the average of those products that were measured, that were X and Y measured in a standard unit. That's what it is. It's a complicated kind of equation, but once you remember what it was, it will make sense. This correlation is also called Pearson's coefficient or Pearson's correlation coefficient as well. So if you've heard multiple different terms for correlation, they all mean a correlation, and they all follow the same formula. If we don't want to standardize the data in a way that every column has a standard deviation of 1, but we want to make sure that they're zero-centered, but they keep their standard deviation, applying the similar formula is going to give us covariance. Covariance is basically meaning that remove the means, multiply them, and then take the average. And this is the covariance. And covariance is equal to, obviously, based on the equation, is equal to correlation times the standard deviation of X times the standard deviation of Y. These are repetitions from data 8, just so that you know where that correlation was coming from when we were calculating the slope, and kind of getting a sense of the fact that we needed to have correlation in order to figure out the relationship between X and Y. What we also know is that the correlation shows us the linear association. It does not show us nonlinear association. It does not show us causation in any sense. It just shows us the linear association or the degree of linear association between 2 variables, X and Y. And when the correlation is high enough, then in that case, it will make sense to just run simple linear regression or any regression analysis. Otherwise, if you don't see a linear relationship between 2 variables, why would you go and model it using a regression line? A regression value is always between -1 and 1. You can prove it because we standardized all of these data points. You can prove that applying the equation is going to give you always a value between -1 and 1. When R or the correlation is close to 1, that shows a perfectly positive linear association. When the correlation is equal to -1, that's equal to perfect negative association. What is positive? What does negative mean? Positive means that by increasing X, Y is also always increasing. So that's a positive slope, right? Negative correlation means that by negative, a strong correlation means that by increasing X, your Y is going to decrease. So that's a negative slope. And that's why correlation that you have is going to control whether you're going to get a positive slope or a negative slope in your data set or in your linear regression. When correlation is equal to 0, it shows that we have a weak linear association. It doesn't tell us that there is no association between them. It just says that the linear association is weak if you're concerned with linear association. And obviously, I said that linear association does not mean causation in any sense. It just means linear association for our purposes. When R is equal to 0, we would also say that the two variables are uncorrelated, meaning that there is no correlation between them. There is no reason that one increasing or decreasing one is going to have any influence or is going to show any influence on the other one. So there is no correlation between them. We would say that they're uncorrelated. So we said that this correlation is a value between -1 and 1. So that's what I'm showing, that the absolute value of R is always less than 1. And here are some examples. For example, in the first case, you're seeing that there is absolutely no clear sign that there is correlation or linear association between X and Y, right? So take the X-axis always as X and the Y-axis as a second variable. So it looks like that is randomly distributed. So that's why you're seeing that the correlation is also a very small value. Here in this case, we're seeing a significant positive correlation or a linear association between X and Y. That's why it's also shown by this value that's very close to 1. In the third case, what you're seeing is that as we're increasing X, the Y decreases, right? Roughly Y decreases. There's a little bit of noise, obviously, but what we're expecting is that we're expecting to have some linear association, but the linear association is negative. And the value that we're seeing here is -0.7. And comparing -0.7 with 0.95 that we had in the second case, you're seeing that the linear association is slightly weaker because we have some spread around, some spread in the data or some noise in the data that is kind of keeping us from having a perfect linear association. But despite that issue, we still see some linear association. In the last case, what would you guess the correlation be? The correlation, so this is kind of where I'm going to try to re-emphasize that what we're seeing in this case is that there is some relationship between X and Y, right? What we're seeing, in fact, is a quadratic relationship. But since it's not a linear relationship, if we go ahead and calculate correlation, it's going to give us a correlation of close to 0. Because again, there is no linear pattern between X and Y, but there is nonlinear pattern that can be captured using other methods or other kinds of modeling that we can do. So moving on and kind of talking about what does it mean when we calculate correlation. When we have correlation of R, in a simple linear regression simple linear regression word, and when our data is zero-centered, meaning that when our data is zero-centered, our regression line is going to pass through the origin. And when we talk about the correlation, that means that by every 1 unit increase in X, the Y value is going to increase by R units. And again, notice that if R is positive, that means that it's an increasing trend. When R is negative, that means that that's a decreasing trend. That's a negative slope. And that's how you can make sense of what's happening in the regression kind of line. But we don't want to live in the standard unit word. What we want to live in is in the original unit or the original kind of composition of the data set that we had. So what we're going to do is we're going to move back all of our data sets or data points into the original units that they were, meaning that our data point or our a regression line is going to pass through average of x and average of y instead of passing through the origin, right? Again, because we removed average of x from all of the x values and removed average of y from all the y values. When we add it back, then it will basically push all of the data points by a factor of average of x and average of y, and that's why the origin is going to move to the point that corresponds to average of x and average of y. What you're seeing here is that x is scaled appropriately. Here we would say that for every standard deviation unit of x, y is going to be changed by r times the standard deviation of y, right? That's how, again, you're scaling across the x, scaling across the y, because previously you divided by a standard deviation of x and a standard deviation of y. If you multiply that back, this is what you're going to get. 1 is going to be multiplied by a standard deviation of x, and r is going to be multiplied by a standard deviation of y. That's why the scale is going to be different. So the equation that we will have, and this is the equation that you had seen in data 8, is that what we have is the equation for this line is y hat, or the prediction for y, minus y bar divided by a standard deviation of y. This is kind of moving all of these, all of the points or all of the equations from the top equation down to the bottom equation, but moving it to non-standard unit. So when I had y hat before, I'm going to here say that this y hat was measured in a standard unit, but the non-standard unit is going to be this y hat. So y hat minus average of y divided by standard deviation of x. I'm moving r down, and then I'm also saying that the way that I calculated x in the standard unit was that x minus x bar divided by standard deviation of x. That's the equation that we'll be working with. If I move this equation to this other slide and try to simplify and just make sure that y hat remains on one side, and then everything else is going to be remained on the right-hand side, and then I'm basically trying to get the coefficient, get a hat, which is your intercept, and also b hat, which was your slope, then we can basically figure out what is the intercept equation and what is the slope equation in our case. So let me start doing that. From this point and on, I might write equations on this slide, but when I publish the slides are going to have animation, so you can actually walk through the animation and figure out all the steps. So what I'm going to do in order to simplify this equation is that I'm going to multiply both sides by a standard deviation of y so that I can get rid of the denominator in the left-hand side. So what I'll have is y hat minus y bar is equal to r times the standard deviation of y multiplied by x minus x bar divided by standard deviation of x, right? So my goal is always to have this form, right? In order to get to that form, I just need to move also y bar to the other side of the equation. So what I'll have is that y hat is going to be equal to r times the standard deviation of y divided by standard deviation of x multiplied by x minus x bar plus y bar, right? So far, so good. The only thing that now I need to do is to isolate everything that is multiplied with x into one coefficient that I want to use as b hat, right? So I want to have one term that has all the things or all the coefficients that are multiplied with the variable, and every constant term that's going to be added to this core term is going to be separate. So meaning that I want to actually split and take out x from this parenthesis or this equation right here, which will tell me that y hat is going to be equal to r times the standard deviation of y divided by standard deviation of x times x, right? And then the other thing that I'll have is y bar minus r times the standard deviation of y divided by standard deviation of x times x bar, right? I just rearranged some of the terms. So if we go ahead and take a look at what we had there, the coefficient that's multiplied by x is going to be my slope, or is going to be my b hat, which that coefficient right here is exactly what we're seeing right here. So the slope is going to be, I'm going to write it here, that the slope is going to be equal to r times the standard deviation of y divided by standard deviation of x. This is what we had seen before. We just gave it to you in data 8 that the slope is equal to r times the standard deviation of y divided by standard deviation of x, but this time we actually derived it for you from the fact that what was correlation, what was the standard unit, and then what is the actual shape of the line that we have with every one standard unit kind of increment in x, y is going to be increased by r times the standard deviation of y, and then technically that's how we arrived at this equation. Then the only other thing that I need to talk about is the intercept. Everything else that's remaining here is going to be intercept. And I'm going to write that out, that this is y bar minus. And what you're noticing here is that this term right here is exactly what I had for this slope. So I can directly say that that term is equal to slope. So I have y bar minus slope times x bar. And that was the equation for the slope that we had from before, that the slope is always y bar minus r times y bar minus a slope times x bar. And then obviously what we have for the residual is that y residual or the error in prediction for data point I is equal to the exact value minus the predicted value yi hat. And I use hat because that's the predicted value and that's not the exact value that we calculate. And then yi hat, you can actually derive it using this equation, which now we derive both the slope and intercept, and we can directly have the equation of the line and actually go ahead and calculate it. So the goal that I have for today's lecture is actually go ahead and derive all of these equations one more time using calculus. And then we'll see how we can actually do that and what's the formal way of us defining how good a model can be and how we can objectively evaluate it. So let's go through the modeling process. So this is the process that we will go over every time that we want to build a model. Up to the end of the Data 100 lecture, every time that I want to talk about creating a new model, I'm going to follow this same modeling process. And let me tell you what this modeling process involves. The first step of the modeling process is that every time that we start doing a modeling, there is going to be a data set. Your data set is going to have one or more attributes or inputs that we're predicting, and then it is always going to have a y or a target variable that we're trying to match it to. So each row of our data frame that we're providing you is going to be an observation, which one piece of that is going to have inputs, features or attributes that we're going to model. In the simple linear regression world, we're assuming that there is only one input that we're trying to match to the target. And then the second instance is always going to be output, outcome, or target variable. So we're trying to use xi's in order to predict yi's as accurately as possible. Again, in simple linear regression, we're only concerned with having one feature or one input, and then we always have one target value. But when we would move to multiple regression, that's the case that we will have multiple different features, and we're trying to combine them together in order to predict the output or target variable. But always the target variable is going to be a single value for every row of observation that we might have. Every time that we're referring to the fact that we're doing the prediction, we're going to say that the predictions are going to be y hats. For every row, there's going to be a yi hat that we're predicting. Again, here I have n rows, so the predictions that I have is going to be y1 hat, y2 hat, and then so on and so forth until yn hat. In terms of the models that we will build today and also in the next couple of lectures, we're going to start by building a simple linear regression. So simple linear regression is having an equation like this, that there's always an intercept term, theta 0, and then there's always the slope that we're always referring to that as theta 1 times input, and then we will combine the two terms in order to get the prediction. We will also see other types of models in Thursday's lecture and also next Tuesday that is going to be constant model and multiple linear regression that we'll talk about them later. I want to put out there that all the models that we'll be discussing, they're called parametric models because using the data we will learn parameters of the model. All of those theta values are parameters that once we know those parameters and once we know what kind of model we use, then we can directly do the estimation of each one or the calculation of each one of the estimated values as accurately as possible. So these are the parameters that we use for the modeling purposes, and that's why they're parametric models. When we say that we have all of these parametric models, the only parameters that we have are all of those slope and intercept and those coefficient values. Everything else is going to be input or the features that we're using. So in other words, the X and Y values are not our parameters. So only the theta values are our parameters. When I say that I use a parametric model that is parameterized by the theta value, then I will go ahead and derive what is the optimum set of theta values that is going to be as accurately as possible modeled through my entire data set. We call them theta hats. Hat on top of theta means that there was a model that now this theta parameter for that model is the optimum set of parameters. And I'm going to show you what that means if a model is not optimum, because technically when you define a model parameter, or when you're defining a parametric model, you're just defining a function or a mathematic function. You're not trying to find out what is the optimum mathematic function that models your entire data set. So this is what it means. When we have a model, we're basically trying to define the family of functions that can be used in order to model our relationship. We would say that, okay, if I have the model parameters to be theta, then my model equation is going to be y hat equal to theta 0 plus theta 1 times x. When I say that I have the best optimum theta value, I will go ahead and put a hat on top of it, which basically means that this time, if you go ahead and calculate y hat values using these optimum values, this is the best prediction that you can have on average on the entire data set that we have. Again, this right here is going to be a family of the models that can be applied to our data set, but there's only one set of values that is theta 0 hat and theta 1 hat that are going to be optimal. Okay, and that's what we're going to be after. In data 100, one thing that you notice is that we're moving away from using A and B for linear regression, and we're moving into the theta 0 and theta 1 world. And that's very important. We're not using theta 0 and theta 1 because we think we're fancy, but this is because what I can do is that if I keep adding features or attribute to my model, then what I can have is that I can have a coefficient or a theta value associated with each one of those attributes, and I can combine all of them into a vector. So for example, in this case, what I've done is that I'm saying that my model uses theta 0 and theta 1. Let's combine them into a vector of theta. And you pass me theta or you pass me theta hat. I know what model you're using. I know what parameters you're using, and I can go ahead and use those parameters, right? Instead of just go through A, B, C, D, and so on and so forth. This way, just using the subscript of I, theta 0, theta 1, theta 2, and so on and so forth, what we can do is we can consolidate them into a theta vector, and then we can index into the relationship between which feature has what weight more accurately or more easily. So that's kind of the notation that we'll be using. I said here we have a parametric model. We have seen non-parametric models before. So some statistical models do not have parameters. For example, we have seen KDEs. KDEs were models or kernel density estimate. But we did not set any parameters. We would just estimate alpha, and then we would just run a process, and we would have KDs. K-nearest neighbors is also another model that you did not need to set parameters, or there was no parameter to learn. So those are the cases that there are models that are non-parametric. There are models that are parametric. What we're dealing with is parametric models. And what we're going to do throughout this multiple lecture is to learn those parameters, how to optimally learn those parameters, how to derive those parameters so that we can uniquely have our own model to work with. So now that we know the terminology and we know the notation that we'll be using, let me walk you through the modeling process. Every time that we want to build a model, irrespective of what model you're building, you first need to choose the category of model that you want to use. So for example, for today's lecture, what we would say is that our model is going to be a simple linear regression, and we might change our mind in the next few lectures, and we will keep using different types of models. But the first step is that you figure out what framework you want to use. The second step is to choose a loss function. What is a loss function? Loss function is a function that will tell you how good or bad your predictions are. And I'm going to objectively define what this loss function means and how to choose a loss function in the next few slides. Once we have the model and we have the loss function, we'll go through an optimization process. This is the fun part that we'll actually go ahead and try to optimize our loss function in a way that we find the best set of parameters for our model. So we go from having theta up to having theta hats. And once we have theta hats, we have our model, we have optimized model, and we're ready to go. Once we have our theta hat and we fit the model and we find the optimum parameters, we need to evaluate the model. So we're going to briefly talk about what are the evaluation criteria that we'll have after we have the model to make sure that our model is performing well on the data set that we have. So let's start with choosing a model, which should be simple in this case. We're choosing simple linear regression for the purpose of today's lecture, because today's lecture is just basically setting you up with all the new notation and the new terminology that we're using. We're going from A and B, we're going into the world of theta, so we're using theta 0 as my y-intercept and theta 1 as this slope that we're using. So what I said was that this theta vector that we have is defining a family of functions. So what that means is that if you are saying that you have a theta vector and you pass the values of theta 0 and theta 1 of that theta vector, you pass the input, you have the prediction. So think about that as a machine that throughout the modeling process will try to find the parameters for this machine that gives us the best estimations, right? So that's what it means. That what we have is that the parameters are sitting in the middle, and we're trying to find the optimum set of parameters in the middle to get the best estimations, the best estimations as much as possible. So one thing to notice here is that I'm using also hat on top of the estimations, right? And I was using hat one more time when I was putting it on top of thetas. This is kind of operator overloading that I'm using. So when hat is on top of y, that means that's an estimation. When hat is on top of, or that's the prediction. When hat is on top of the theta, that means that that's the optimum set of parameters for the model that I'm using. So the first step is done. We have a simple linear regression. We know that the pattern of the function is going to be that two parameters are going to be given, and then we can calculate the prediction of y, which is y hat, using theta 0 plus theta 1 times x. Now we need to get into what is the loss function and how can we define how good we're matching to the target values based on different models that we have. So we are going to actually follow a certain process that defining a cost function and optimizing the cost function up to the point that we get to the optimum set of parameters that I'm referring to as theta 0 hat and theta 1 hat. So choosing a loss function. How can we quantify how good or bad a function is mapped to our data set? So for example, what you're seeing here is that I have 3 lines. Again, remember that that machine in the middle was defining a family of lines. So here in this case, I'm just throwing out 3 random kind of sets of values for the theta vector. So here, theta 0, theta 1, theta 0, theta 1 for 3 separate lines, and then I draw all of those lines. So what we're wondering is that just looking at the shape of these lines and the distribution of the data, which one of these models are more accurate? And then think about how you're going to measure in your mind what accuracy means. This is your first slide of the day. Which one of these lines matches the data set more accurately? Okay, it's kind of clear that the blue line is matching our data set more accurately. And the process that probably went in your mind was that, okay, I'm looking at the miscalculations or mispredictions. I'm looking at how far the points are from each one of those lines. And it looks like that when I'm looking at the distances from the line, the blue line has the minimum distance on average across all of the points in the data set. Versus, for example, if you're looking at the red line, if you want to calculate the distances of all of the points from the line, that's a very high error that we're accumulating throughout the entire data set. So we're defining the loss function in the same way. We would say that we're going to take a look at the predicted values. We're going to take a look at the real values. And we're going to have a single value that assigned to how bad the predictions are. So what we would say is that if y hat is close to y, we would give you a low loss. We would say that you did not do that badly, and then we would give a value in r, which is a small value. But if y hat is far from y, in the cases that the predictions or the line was far from the actual individual values, we would give a high loss. That's the general idea. Per given data point, we would calculate loss, we would calculate the error, and we need to have a function that will actually penalize the model based on each one of those miscalculations or misestimations that it has. So the choice of the loss function is really important. In Data 100, we're going to cover, I think, 3 or 4 different types of loss functions that will actually do exactly the same thing. It will tell us how bad our predictions were, and it will basically tell us that it will penalize us more if our prediction is far from the actual value, and it will penalize us less if our prediction is close to the actual target value. But the choice of the loss function really depends on multiple different metrics and different types of modeling that you're doing. For example, if you're doing a classification task versus a regression task, the loss function is going to be very different. If you're doing a classification task, for example, if you're doing cancer identification, in a sense, you really don't want to miss any potential cancer patients. So in those cases, you really want to have a different kinds of loss function that accounts for all of those cases as well. So we're going to take a look at all of those considerations when we go into evaluating the models a little bit more, just putting it out there that when I talk about loss function today, I'm going to introduce 2 loss functions, but those are not the only loss functions that we use. Depending on the use case, the loss function can be different. So loss functions of the day. You might have seen these equations before. One loss function is called L2 loss or a squared loss. One loss is called absolute loss or L1 loss. Order 1, order 2, right? Think about them like that. So the squared loss basically says that go ahead and take a look at the actual value, subtract the predicted value, so meaning that calculate the residual and go ahead and square the residual. So anytime that you saw an error, score that error, which basically means that if your error is very small value, I'm scoring it and I'm even making it smaller, right? So if you're taking a look at the residual being a value between 0 and 1 and you score it, that's even going to get smaller. So it's not going to be penalized as much compared to the case that, okay, if you have 100 units of residual, it will square it to penalize you even more. So the penalty right now is going to be 10,000 in that case, right? So that's kind of L2 loss or the second order loss that we have. The absolute loss just looks at the residual and calculates the absolute value. Again, meaning that if it's the small, it's just going to be that same absolute value of the residual. If it's 100 unit of residual, it's just going to be same 100 unit. It's not going to be penalized any further. But in both of the cases, we're penalizing. And in both of the cases, what you notice is that the loss is always a positive value because it's a cost, right? So we want to give a cost. We don't want to give a negative cost. So in the cost in both of the cases, in our case, is positive. So what does it mean in the language of linear regression? That means that I'm going to go ahead and replace, in every instance that I have y hat, I'm going to replace it with the equation for the simple linear regression. So here I have y minus y hat. So here my loss for simple linear regression based on L2 or a squared loss is going to be y minus This right here is y hat, and then the squared. Same thing for the L1 loss. We just plug in y hat, and then we have the equation. Notice that what I have right here is the loss or the cost for a single data point. But what we want is we want to have a line that matches all of the data sets as all of the data points in a data set as closely as possible. So in that case, what we would do is we would go ahead and take average over all of the data points. So let's go through two more slide questions to make sure that we're all on the same page with respect to what is L1 loss, what is L2 loss, and so on and so forth. So the question is, if you want to penalize large residuals more than the small residuals proportionally, what is the loss function? Which loss function is more ideal? Do you want to use absolute loss or do you want to use the squared loss? Looks like a squared loss is the winner because of the example that I gave, right? So if you really want to penalize large miscalculations or mispredictions, you really want to use the squared loss in those cases. What would be the drawback if we penalize large deviations so much? There is one drawback in that case. Just a quick hint would be an outlier. Anything about outliers might be an issue here. Yeah. Mm-hmm. Yeah. So the answer was that the outliers are generally far from the trend of the data. And the model, if model wants to try to avoid having that squared large loss that it might incur, it might tilt the line or the model from the actual trend that it needs to be to the trend that's kind of meets halfway in between, so that it gets some small loss on the actual trend of the data and also gets closer to the outlier data point that it has. What about this question? Why don't we use the actual residual values directly? Why do we square them? Why do we calculate absolute value? Why do we want all of the cost values to be positive? Why do we want to get rid of negatives? Sum will be 0. Residual sum to 0. That is correct. Okay, they don't cancel out. So that seems to be the right trend. But the issue that we have when we try to just use the actual residual values is that some residual values are positive, some residual values are negative, right? This is what we saw before. And if we just actually get the residual values and sum them up, the issue is going to be they're going to cancel each other out. And again, we need to calculate the cost and aggregate in the entire data set. So that's why we really want to make sure that all of them are positive cost values. And that's why we're using either absolute loss or a squared loss in all of these cases. I said we need to make sure that we calculate the loss for all of the data points. In fact, the way that we do it is that we will go ahead and sum up all of these loss values for all of the data points. So you see yi hat, that means that the prediction for data point I, and assuming that we have n different data points, we will sum up all of those loss values that we have, and then we will divide it by n, which is going to be calculating the average, right? Summing up makes sense because I want to take a look at the entire data set. When I'm dividing it by n, this is the case that if I'm comparing the model performances on different data sets, I don't want the size of the data sets to be influencing my decision about which model is performing better, right? Or which model is performing. Objective function that we'll be using in order to train a model and find the optimum set of parameters that we have. One note is that what you notice is that this function is a parametric function. It's parameterized by theta, meaning that if you give me different theta values here, I'm going to give you different y hats. And by having different y hats, you're going to have different losses for the data points. And then once you have different losses, you're going to have a different overall cost or the overall average loss. So kind of notice that this function, depending on the theta, is going to change. And our goal in this case is going to be to find the theta value or the set of theta 0 and theta 1 values that minimizes this cost function, that goes through all of the data points as closely as possible on average and have the minimum average residual values that we have. Okay, does that make sense? So this cost function is a really important cost function. Again, it's parameterized by theta, meaning that depending on the theta value, the value of the cost on the data set is going to change. And why is it going to change? Because when you change the theta value, you're effectively changing the model. When you're changing the model, your cost function is going to be different because your predictions are going to be different. So think about this function as a function that evaluates the entire family of the lines that can pass through your data set. So when we go ahead and plug in for that loss function and plug in L2 loss, you can see that effectively the empirical risk is going to be 1 over n times the summation of yi minus yi hat square, and we call that mean squared error. And if we plug in L1 loss instead of this loss function into the empirical risk equation, this is going to give us 1 over n times the summation of absolute value of all of those residual values that we have. So MSE versus MAE. In the next lecture, I'm going to come back and play with optimizing both of these functions. And I'm going to show you what's the difference between the final model that we'll get depending on which loss function that we use and which empirical risk function we get at the end. For today's purpose, what I'm going to do is I'm going to say that I'm going to use L2 loss, meaning that I'm going to go ahead and calculate the residual square of each one of those data points in the data set, and my entire empirical risk function is going to be MSE or mean squared error. Again, this is the mean and this is the squared error of all of those predictions that we have. This is yi, this is yi hat that we have based on the simple linear regression. What you know from data 8 is that you know that they called this the linear regression that they were teaching you. They called it least squares regression. We also used exactly the same terminology here. Effectively, simple linear regression pattern or function together with the optimization function that is mean squared error is called least squares regression, because we're trying to find a function that minimizes these squares of the errors that we have over the entire population. So now down to the fun part. I said that if you have the two parts in the model, you have the model kind of pattern or the template, which in this case is simple linear regression, and you know what kind of cost function you're using, then everything else is going to be easy. Fitting the model is going to be easy. What I'll do is I'll basically tell you that what does it mean to fit the model. When we say that we want to fit the model, that means that I want to find the combination of theta 0 and theta 1 values that are giving me the minimum function or the minimum value for the right-hand side of this MSE function. So in order to do so, what you know from your math courses is that I need to calculate the derivative of this function with respect to theta 0, set it to 0. With respect to theta 1, set it equal to 0. Find those optimum points. And those optimum points, theta 0 and theta 1, are going to be exactly my theta 0 hat and my theta 1 hat that I can use, right? So the next few kind of, or 5 or so minutes is going to be me deriving all of these partial derivatives for you. It might sound scary, but this is kind of the first starting point for you to get comfortable with this entire pipeline and actually appreciate that all of the math courses that you learned so far is actually going to come in use in machine learning, because machine learning is all about having very strong calculus and linear algebra background, and this is the place that you will see where it will become handy. So I'm going to start by taking partial derivatives. So moving that equation right over here. It says audio is out. I don't think it's out. It's on? Okay, cool. So I have the objective function, and let me reiterate what this objective function was. Remember that this objective function is calculating the average over the scores of the errors, right? So this is the error inside the parentheses. What you're seeing is yi minus yi hat, which is the residual to the power of 2 that I'm calculating, which is mean squared error that I want to calculate. So I'm going to take the derivative with respect to theta 0, which effectively what that means is that I'll do the normal derivative, but I'm just assuming that anything except for theta 0 is going to be a constant value, right? And there are a couple of steps that I need to do first. One is that I'm taking the derivative of a summation term, right? And we know that the derivative of sum is equal to sum of the derivatives. So I'm going to take out the coefficient and the summation out of the derivative so that things are a little bit easier and cleaner. So moving this summation out is going to give me 1 over n times the summation of I from 1 up to n of the derivative of what I had, which is yi minus theta 0 minus theta 1 xi to the power of 2 with respect to theta 0, right? So first step is easy. I just basically took out the summation and said that the derivative of a summation is equal to sum of the derivatives. So I'm taking sum of those derivatives. So the next step is that you're seeing that I have a second order function here. If I want to take a derivative with respect to theta 0 inside is raised to the power of 2. So you know that in this case, I need to apply chain rule first, meaning that I basically try to take the derivative of the outer function and then take the derivative of the inner function, which in this case is going to be me rewriting the coefficient right here, 1 over n times the summation of I from 1 up to n of. So if I apply the chain rule, that's function to the power of 2. If I take the derivative, that's equal to 2 times function times derivative of function, right? If you think about this as function to the power of 2. So what I'll do is I'll say that 2 times the function, which is equal to yi minus theta 0 minus theta 1 times xi. And then what is the derivative of this function with respect to theta 0? So again, assuming that everything except for theta 0 is a constant term, so the only term that I have to take the derivative is negative theta 0, and derivative of that with respect to theta 0 is going to be negative 1, right? This step is easy. I'm just going to clean everything up and just simplifying constants here. This is going to give me negative 2 over n, just taking all the constants out, summation of I from 1 up to n of yi minus theta 0 minus theta 1 xi. So we're done with theta 0, or taking the partial derivative with respect to theta 0. Let's go ahead and do exactly the same thing for theta 1. And then because I need to take derivative with respect to both of them, set both of them equal to 0 and then solve it. So we need to have both of the derivatives ready to go. So I'll do exactly the same thing, that the derivative of sum is equal to sum of the derivatives. So I'm taking out the coefficient 1 over n and the summation out of the derivative. So it's going to give me 1 over n times the summation of I from 1 up to n of the derivative of, yes, yi minus theta 0 minus theta 1 xi is squared with respect to theta 1, right? Same story here, right? So the story is that I'm taking the partial derivative with respect to theta 1, and theta 1 is the only variable that I'm concerned with. Everything else, I'm assuming that is constant, but theta 1 is raised to the power of 2, right? And it's within a function. So if I want to take the derivative of this function to the power of 2 with respect to theta 1, this is going to be equal to 2 times function times the derivative of function with respect to theta 1. And that's exactly what they'll do. And I'm assuming that this is this function f that I'm calling. So I'm going to apply the chain rule exactly. So 1 over n times the summation of I from 1 up to n of the function yi minus theta 0 minus theta 1 xi. Now the derivative. So what is the derivative of that green term with respect to theta 1? Yes. Negative xi is the derivative, right? So negative xi is my derivative right here. So I'm just going to go ahead, simplify constants one more time. So here's going to give me, sorry, I missed the 2. So it's 2 times f times whatever. So this is going to be negative 2 over n of the summation of I from 1 up to n of yi minus theta 0 minus theta 1 xi times xi, right? Look at both sides. Look at that function f thing that's in common between them. So one is effectively telling me that if I go ahead and set this to be equal to 0, the left-hand side is effectively telling me that the summation of all of the residuals should be equal to 0, because that's residual. And that's why they were canceling each other out. That's why they couldn't be a cost function, right? This is telling me that at the point that theta 0 is optimum, the summation of residuals should be equal to 0. And then the right-hand side is basically telling me that the summation of residuals times xi's should be equal to 0, right? We're going to get to that. And what I need to do right now is that I have 2 equations and I have 2 unknowns. And what are the unknowns that I have? So I have 2 equations. There's one unknown, theta 0, and there's one unknown, theta 1. I set both of them equal to 0, and then I solve it for the optimum theta 0 and optimum theta 1, and that will give me theta 0 hat and theta 1 hat, which are the optimum values that we want. Again, you'll get this slide with animation and fancy animation, so you will get a clean version of all of these. So this is where we left off. So remember, that was the equation from the left-hand side. The second row is the equation from the right-hand side. So the summation of residuals is equal to 0. Summation of residuals times xi equal to 0. What I need to do is I need to just go ahead and use these equations that I'm calling them estimating equations, because I'm using them in order to estimate optimum theta I values in order to I'll solve them in order to find out those optimum values exactly. So let's go ahead and do that. So these are the 2 equations. 1 over n times the summation of yi minus yi hat is equal to 0, and then the second equation is on the right-hand side. What I'll do is I'll derive the first step. So deriving the first step means that what does it mean for this equation to be equal to 0? Is there any way that we can simplify it further? So what I'll do is I'll go ahead and try to decompose all of these 3 terms that are inside the parentheses and inside the summation into separate terms. Meaning that what I'll do is I'll say that this equation is equal to 1 over n times the summation of I from 1 up to n of yi. That's the first term. And then I'll say minus 1 over n times the summation of I from 1 up to n of theta 0 hat, right? And then minus 1 over n times the summation of I from 1 up to n of theta 1 hat xi equal to 0. Okay. Can someone tell me why my thetas right now turned into theta hats? Because it's optimized to 0. Remember in the previous slide, when I was on the previous slide here, actually, yeah, right here, when I was driving all of these values, the theta 0 and theta 1, they were just normal theta 0 and theta 1 of the function. I actually derived it and calculated the partial derivative with respect to theta 0 with respect to theta 1. At the point that you actually set it equal to 0, which is what we have right here, I set this equal to 0, then theta 0 will become theta 0 hat, because that's the optimum theta 0. And theta 1 will become theta 1 hat, because I'm also setting this one equal to 0, right? So that's at the point that you're calculating the optimums and you're finding the exact optimum values by setting the partial derivatives equal to 0. That's when theta 0 and theta 0 and theta 1 will turn into theta 0 hat and theta 1 hat. Let me go back to this place that we were. So that's why I have theta hat, theta 0 hat and theta 1 hat right here as I'm solving. And then at the end, we'll get to what is the actual value for theta 0 hat and what is the actual value for theta 1 hat. So let me continue. What is the value? What is the simplified version of 1 over n times summation of yi values? That's y bar. That's average of y values, right? The other thing, what is the simplified version of this? Theta 0 hat is a constant value. I'm summing it up n times. So this is going to be n times theta 0 hat. And then I'm multiplying 1 over n. So this is equal to just theta 0 hat. So the second term is theta 0 hat. And then what is the last term? So the last term, there is no easy way to simplify it except for saying that I'm going to pull out theta 1 hat outside of the summation because it's a constant value. So then I'll have theta 1 hat times the summation of I from 1 up to n of xi's, which this one right here is also going to be x bar because that's the, sorry, there's 1 over n. 1 over n times the summation of xi's is going to be x bar. Again, setting it equal to 0, kind of cleaning up what I wrote here. Y bar minus theta 0 hat minus theta 1 times x bar is going to be equal to 0. Right? What does this tell you? This one is telling you that, remember when I was calculating the y-intercept, I was saying that theta 0 hat is equal to y bar minus a slope times x bar. This is exactly that. This is deriving exactly the same equation for the theta 0 hat that we had from before. But we just derived it through the crazy sequence of defining the simple linear regression to going through defining the cost function. We chose mean squared error as our cost function. We calculated partial derivatives. We set partial derivatives to equal to 0 in order to find out what is the optimum theta 0 value and the theta 1 value. And then it just happens that if I simplify the first function or the first derivation, it's going to tell me that your theta 0 hat is going to be equal to y bar minus the slope times x bar, which is what we know from slide 3 of today's lecture. But now we systematically derived it, and now we have a formal way of defining the objective function. The only thing that we need to now do is to figure out what is this theta 1 hat. But we still have two equations. We just looked at one of the equations. If we combine the two equations together, which I'm not going to try to derive it manually, but I'm going to walk you through the steps, it's going to help us to find out theta 1 hat. The trick that we're going to use here is that we're going to take equation 2. We're going to subtract equation 1 times x bar from it. This is just an algebraic trick that you don't need to know and you should not be expected to know in the exams, but this is what I'm using in order to derive how we can find the theta 1 hat. So if I go ahead and do the calculations, so what you're seeing is that this is equation 2 right here that we're seeing. This term right here is equation 1 multiplied with x bar, or the average of x. You can kind of guess why I multiplied it with x bar. This is because the equation 2 has that xi term dangling there, and it just need to have something of the nature of x to accompany it. And that's exactly what I'm using it. So what I can do right now is going to be, I'm factoring out all of the yi's minus yi hats because that's the term that's in common between them. So then this is how this is going to turn out to be yi minus yi hat, and then xi minus x bar, and then multiplied, sum up, average is equal to 0. I'm going to take one more step. I'm going to substitute yi hat here with the equation for yi hat. So the optimum yi hat is going to be theta 0 hat plus theta 1 times xi. So I'm going to use that. And what I'm going to use again is going to be, I'm going to replace theta 0 with the equation that we just derived, right? the equation for theta 0 was that it's y bar minus the slope, which is theta 1 hat times x bar. So now what you're seeing is that I have one equation. All of the variables are known except for theta 1 hat. And what I can do is I can just keep simplifying it in order to find out what is theta 1 hat from this equation. So if I keep simplifying, which I'm not going to go through the steps, it's going to give us this equation right here. So what is this equation? This equation right here is telling me that okay, so you have yi minus y bar, you have xi minus x bar. On the right-hand side, you have theta 1 hat multiplied with the variance of x. So kind of a reminder from what we know from correlation, you know that the correlation was equal to this equation right here, which sounds similar to what we have in the left-hand side. So what we can do is we can say that the left-hand side right now is going to be equal to r times the standard deviation of x times the standard deviation of y, because the only thing that this equation is missing compared to this equation is these denominators right here. So the left-hand side of this equation is r times the standard deviation of x times the standard deviation of y. The left-hand side is my theta 1 hat times the variance or standard deviation is square of x. And then what's happening here is that I only have one unknown. I can directly solve it. Now theta 1 hat is going to be equal to r times the standard deviation of x over standard deviation of y. This kind of sounds like magic, but now we formally defined how actual machine learning people do modeling. They don't guess. They basically have a mathematical objective function that they define. They define the family of functions or the model pattern, which is what we did. We defined what is the equation for simple linear regression. But we said that, okay, depending on the theta 0 and theta 1 value, it's going to be a different function or a different line that we're mapping. How do we find out how good that function is? We define the cost function. We actually use mean squared error. We actually went through calculating partial derivatives in order to find out the optimum values for theta 0 and theta 1, which got us the theta 0 hat and theta 1 hat that we have. So this is where we are. What we got at the end was the two kind of final notes that I told you when I was doing the derivation. I said that the average of residuals is equal to 0, or the summation of residuals is equal to 0. And I also said that the residual multiplied with the xi is equal to 0. I think on Tuesday of next week, we're going to talk about the fact that this means that the residuals are orthogonal to the predicted variables. And we're going to see what that means. This is two vectors orthogonal to each other, and that's how the shape of the line is always deterministically calculated once you have all of the data points that you have. We have 2 more minutes, but I just want to throw it out because you need this for discussions that are happening today, and that's about evaluating the model. Your TAs are going to talk about evaluating the model a little bit in discussions today, but effectively that's the last step of the data of the modeling that we're going to go through. There are 3 things that we're doing generally when we're going to evaluate how well the model is performing. The first thing is that a lot of time we would go ahead and visualize the data and we will compute the statistics. Again, we will calculate the correlation coefficient. If the correlation coefficient is acceptable, then we do the linear regression analysis. The other way that we evaluate the performance of the model is that we'll calculate mean squared error and we'll calculate the square root of that. That's called root mean squared error. And the reason that we calculate the square root of it is because we want to turn the error into the original unit of the data. Because the error is in the second order. When we were calculating the square root of the errors, we were squaring the errors, so the unit was in the squared units. So by taking a square root, we're going back to the original unit of the data. So that value is going to be meaningful if you're doing any estimation. The last thing that we will do, and this is what you will see in discussions, is we will visualize your residuals. So when we go ahead and visualize residuals, what we want to see is that if these are the 4 different data sets that I'm dealing with and I'm passing the regression line through them, you can kind of see that the regression line matches 1 or 2 of them perfectly, but it's not a suitable choice for the rest of them. If you go ahead and visualize the residual, meaning that on the y-axis, you plot the residuals, on the x-axis, you plot x, we don't want this residual plot to have any kind of pattern, which is what you're seeing in this first case, that residual plot does not show any pattern, but you're seeing that the residual plot absolutely shows the pattern, meaning that linear regression was not a good choice. Or residual plot in this case also shows the pattern. Also in this case shows the pattern, right? So what we want at the end is that once you build the residual plot, you really want to make sure that the errors are kind of randomly distributed and equally distributed across X and also across the residual kind of dimension. Your T's are going to more talk about this a little bit more in the discussion. Thank you for coming. We're going to talk about constant model and more loss functions on Thursday.